Where should I be standing?
Well, I can't see your head anyway, so.
Yeah. Okay. Welcome, everybody. Welcome to Galvanize. It's 6:20, so it's kickoff time. I'll just quickly introduce Galvanize and then hand it over to Parker, your instructor for the evening. For those of you who don't know already, but you probably do, I'm guessing, we're a boot camp essentially. We call ourselves an immersive program for web development. We also have data science immersive and data science master's degree program, and about 173, from what I last heard, startups working out of our space here. So it's a big building. I think it's a beautiful building. It's multifaceted in that there are all these tech startups operating right out of the space next to our students where they're learning and building sort of similar projects and doing similar things. And the idea is to sort of create like a tech ecosystem here. I recognize some of you from Dev Bootcamp, which is awesome. I used to work at Dev Bootcamp. I recognize some of you from Galvanize, which is also awesome, but from our data science program, thank you for attending. And also from Hack Reactor, I recognize at least one person from Hack Reactor. So this is cool. This is cool that we're building the community in this way. Parker and I were chatting, like, I always love to host Learn to Code events here, and Parker had an interesting take on it, which is this, like how to nail your technical interview. So if you give good feedback and if you like really prop up Parker tonight, he's going to keep doing these. So make sure to do that. Yeah, we haven't scheduled another one yet, but ideally this will become a series. Not so secretively, I want that to happen. So thanks for coming, thanks for participating, thanks for learning, and if you can, spread word of Galvanize that we have these education programs here, and tell people to come to our free events and at least get a taste for the space. Even if they never end up attending a program, we don't care. We just want to be a community space, and to help spread word of Galvanize would be a nice residual benefit of that. So enjoy yourselves. Hopefully you'll have enough snacks and water back there, and a reminder too for those of you who came in, the restrooms are like right there. I'm running a little bit of like a tour group for sort of a beginner coding organization tonight. We're just in the next room over, so I might slide in at some point in the back, if that's okay. Cool. Thank you. Enjoy, and welcome again.
Thanks, Andrew.
Parker Lewis, everybody.
Hi, I'm Parker. Yeah, thanks for coming. So have you ever like prepared a lot for something and then instantly felt like you didn't know anything about it? That's how I feel right now. So literally I just feel like they're gonna walk out and like riot and tell Andrew that I'm the worst person ever. Hopefully that doesn't happen.
We're on your side, Parker.
You're on my side, thank you. Thank you. Yeah, I've done this before. I don't know. All of a sudden I was sitting there and I was like, I don't know a single thing. Hopefully I can teach you something, because I do know a fair amount about binary search trees. So Galvanize is awesome. I'm not a salesman. I heard many of you went to different programs, so that doesn't bother me. But one thing I love about my job is that I get to just take a topic that I know nothing about, learn about it all myself, and then go teach other people who want to know the same thing. So that's what I did. Andrew and I talked like a month ago, I was like, yeah, I think it'd be cool to just give some like interview tips to people, and like we just talked about how we can make it into a series, and this is what I chose. Can I get some hands, like who was in some type of boot camp program specifically for web development? I heard there were some data science people in here, but yeah, that's awesome. Thank you for coming. Andrew owes me $1. Yeah, I hoped the title would attract you here. Do you guys mind saying where you're from? Like which programs you're from? I'm not trying to collect data on you. Sorry. Yeah.
Hack Reactor.
Hack Reactor. Okay, get out.
Dev Bootcamp.
GA. Cool.
Hackbright.
Hackbright. Cool.
App Academy.
App Academy. Man, I got all of you guys. Sweet. Cool. Well, I'm very nervous that you're all going to think I'm a loser at the end of this, but hopefully not. What we're going to talk about? We're going to talk about what binary search trees are. I'm going to do another little polling. Yeah?
Do you care if anyone's here for the data science programs?
Oh, yes, data science. Thank you for coming, data science. Yes, you are just as important to us. But yeah, so we're gonna just kind of do an overview. I'm gonna do some more polling to see kind of where people are at, because I like to kind of tailor my talks. I don't want to talk about really basic, boring stuff if nobody cares, or if they already know it, basically. So just an overview / fact gathering. Then we're gonna talk about inserting. We're gonna talk about one search, depth first search, and then we're gonna talk about remove a little bit. Remove's pretty difficult. And then I'm going to show you why, hopefully, you should care. I'm just going to say right at the beginning, my application does not fully work, and I'm really mad about it. But I still think you'll see why binary search trees can be useful. And that's really my first question. Who has studied binary search trees before in some, either on your own or at one of your boot camps or something? Who knows how to apply binary search trees to an actual problem? Yeah, they're just a thing, right? Like, they just live in your computer and, I don't know, eat your memory, and I don't know, right? Like, what do they do? That's why I wanted to tackle this. It was like, I don't care, right? Like, I mean, I care because I really like this stuff. Like, okay, so I was a philosophy major in college. I went to Galvanize as a student. We didn't really teach computer science back then. Now I'm an instructor here. We didn't really teach it, right? And so I really kind of self-taught / with my coworkers, they've kind of helped me along. But I've always, especially with not so much always trees, especially with binary search trees, it's like, why are these things, why does everyone care about these so much? So hopefully by the end, well, you can read it if you want, but I won't tell you what I attempted to make, or almost fully, completely made. But hopefully it will kind of spark your interest and go, oh, okay, it's not just something stupid that we crammed into the last week of our program. Hopefully it's a little more meaningful to you. So what I'm attempting to do is what we call a flipped classroom. I don't know if any of you guys have ever been a part of it, but it's where I talk less than you might expect. Right? You might have come thinking I was going to talk for an hour and a half. You are dead wrong. I cannot talk that much. What I'm going to try and do is talk for 20 minutes, roughly. And then hopefully, if you're all game, please be game. We're going to go to the whiteboards. There are some mini whiteboards up here, and we're going to do this stuff. And we're not really going to be on our computers. I know I have one of my former students here. He knows I love theoretical, right? And that's really where I think this starts. And then you'll see my code. You can look at the GitHub to see the actual implementation of code. But these things, I didn't learn them by coding them first. I learned them by drawing pictures. So I'm effectively going to teach you how I draw these pictures. I hope you like it. So, I initially made this talk thinking I was going to get through like a ton of stuff, and then I was like, man, this stuff takes a little while. So I wanted to get through like all of binary search trees. I was telling, what is your name? Brandon up here that, like Andrew said, if it's a series, I'll do more on binary search trees and in depth a little more. But we're just going to cover it from a level that I describe it as like, I'm in between, hopefully where you guys are, like maybe more beginner, where this stuff is like super theoretical and it just isn't, like it just doesn't speak to you at all, to like my coworkers who are computer science, classically trained, and it just kind of makes sense to them. I feel like I'm somewhere in between, and hopefully I can give you a language to kind of talk about this and just try and see it, hopefully, the way I see it is hopefully helpful to you as well. So, what is a binary search tree? Dave, what's a binary search tree? This is what happens when you know me.
Yeah. Well, first of all, it's a tree, but it only has 2 nodes per, or 2 nodes underneath each. I guess you'd say parent node.
Yeah, 2 nodes for any one given parent node. So tree. Let's start there. I probably should have asked you to start with tree, but thank you. Right? A tree with 2 nodes. Okay, well, what's a tree? So a tree in computer science, computer programming, data structures and algorithms, whatever you want to call it, is really just a bunch of references. Okay? So hopefully we know the difference in a primitive type and a reference type. And I'm mainly going to be speaking in JavaScript language today, but it applies to all languages, right? All languages have a primitive type and some type of reference type. So a tree is just a collection of objects and references to other objects. Right? So here are my pretty pictures, right? And I'll try to make them better. Like I said, we're not going to need computers, so let's get rid of that. I made a tree. It's great. Things about trees. They have a root, the top of the tree. So to me, I'm guessing some people have heard of linked lists. When I talk about linked lists and like stacks and queues, hopefully you've heard some of these words before, right? Sometimes we talk about the front, sometimes we talk about the back. I really try to dispel front and back because it really isolates you into like what I'm trying to think. I really want you to think of how you want to think of it. So like a lot of people will say, why is that the root? It goes down, right? Whereas like, it might look like this, and then that's the root. I don't care. I don't care what you call it. It's called the root, traditionally, so we call this the root. Now, okay. Special about binary trees, right? Binary, as Dave said, we have 2 nodes. Convention on the nodes is that this is less than in some way, the left is less than in some way, and the right is greater than. So we're just going to talk, I like to shave away as much as I can and just talk about like one really simple, one avenue of a tree, or of a binary search tree when I'm first teaching it. Like we might go a little more abstract and take more edge cases in the next one, but just imagine that all we can put in this tree are numbers, and that's all we care about. And we care about ordering numbers. Not practical, right? It doesn't mean anything. We'll see why later. But basically, a binary tree is an object, right? Think of it like a regular object. It holds one thing, or sorry, it holds really 3 things. It holds a value, which is always going to be an integer for us, for these purposes. And it holds a left pointer and a right pointer. Probably not blowing too many minds yet, right? And the left pointer points to a node whose value is less than its parent, if it's the left pointer, right? So the root, what you would say is the root has 2 children. The left node is less than the right, or the parent node. Yeah.
Is this a property of just binary search trees as opposed to just a binary tree?
Binary search tree as opposed to binary tree, yes. The convention for binary search trees are that the left is left. You can do it either way. Again, with the front back thing, you can do it either way, right? But our convention will be left is less, right is more. But thank you, yeah. You can just have a binary tree that has like P and 27, whatever you want in it. It's just we restrict it to get certain characteristics out of the tree. So, got a binary search tree. So, now we can make more nodes, right? It's not just the root that can have other ones, or can have children, as we call them, children. So this one usually I do, 15, 35, 65, 85. So, we're going to learn later why having it this structured actually kind of ends up hurting you in the end, because that's what happened when I tried to make my application, and it ends up kind of hurting you. But it's really useful for getting the basics down, right? You can see this is it's a full and complete tree, right? Every node has 2 children, except for the bottom nodes, which have no children. Very balanced, very full. We're going to work with this structure right now. We'll learn about rebalancing trees another time. We're just going to work within this structure. This is what our binary tree looks like. So what we will eventually be able to do is traverse this tree in such a way that we can get all of the numbers in order. I bet a lot of people have heard that before, right? Like, that's like the ultimate beauty of a binary search tree, is that you can get this ordering of things at the end of it. Try to make that practical towards the end. But know that there is such a way that you can get you can write a function, let's just say, you can write a function that will return, if you give it this tree, it will return the nodes in order, 15, 25, 35, 50, 65, 75, 85, even though it might look kind of crazy. Let's first talk about how to insert into a tree. So let's first imagine, I'll just move over here, that we don't have anything in our tree. What would that tell us? Now we're going to go into some object-oriented terms. Hopefully we're all cool with that. If I have a class of a tree, binary search tree, let's make it more specific. A binary search tree class. It's going to have really one property for any instance of that class. Can anyone tell me what they think it is? What was it? A root. That's all it really needs. It can have a lot more. But again, let's keep it simple. So it's just going to have a root. So if I want to, right, let's say, so again, I'm going to, yeah, I'll do like kind of JavaScript-y, but it doesn't, it's kind of pseudocode, kind of JavaScript. New.
Do you have a darker pen?
Yes.
One back here. Thank you.
Is that better?
Yeah.
So, JavaScript. So now we have a variable that is an instance of our class. Great. So if we looked at bst.root, it doesn't have anything. We're not going to write the actual implementation of the class, just kind of parts of it as we go along. It doesn't have anything. So if we're trying to write some insert method, and let's assume it always gives us a node. You can have it do different things. It could just give you a value and you create the node, but it's going to give you a node that is able to go into the tree. What's the first thing we need to think about when we're running this method? I've already kind of alluded to it. Greater than or less than is close, but not quite yet. What was, did somebody?
First insert the node into the root, and then after that, the next one is for checking.
Right. We need to make sure that there's a root or not. Right? So that's the first thing to keep in mind. Okay? For insert. Is there a root? Okay. So if not, then our insert is really easy. Just insert, or just make this dot root, if it's JavaScript, this dot root equals node, and we're good to go. Right? But if there is a root, what do? We have to take into account less than or greater than. Okay? Cool. So, is it less than? Is it less than? What do we do if it's less? Well, let's get a tree going. Right? Let's say, okay, I insert, let's do like 5, 3, 7, 9. Say we're going to insert all of those numbers into our tree. So we start with 5. Now we're just going to draw the tree, right? Is there a root? Nope. Cool. This is our root. It's 5. Now, what do we do with the next one? So cool, we got that one. All right, well, let's insert 3. But what does that mean? So we check, oh, is it less than, greater than? So how do we do that? So we think, okay, 3 is less than. So you might just think, okay, if it's less than, just make the left of the root 3. And this is, some of you may be like, of course you don't just make the left, or the left less. Sorry, if it's less, make it left. You need to do a bit more than that. But this is where we often start with trees, where it's like, oh, it's just that first thing. Like you just do the simplest thing to make the tree work under the easiest case. And then you can move from there. Because if I never started with this, I wouldn't be able to move forward. So just to encourage you to sometimes do it kind of wrong at first. So let's just go with this. So if it's less, we'll just make it the left one. And then we get one that's greater, right? And then we just make it the right one of the root. And then really quickly, we start to see why this is wrong, right? We get to 9, and we go, okay, well, you just make it the right. But then our 7 goes away. So we want to maintain the integrity of the binary search tree. So what we want is this, right? Because every node's right node should be greater than it itself. So we want this, not this. If 9 were to the left, it would no longer be a binary search tree, so we've wasted our time. So how do we get that? How many are familiar with recursion? Definitely heard of it, right? Maybe done Fibonacci? Who's done Fibonacci? Everyone? Yeah. So this is where recursion is going to come into play. Recursion and trees go hand in hand like no other. Right? Because a tree is made up of trees. So whatever you can do on the first thing, on the first node, you can do on all the rest of the nodes. So I kind of want to leave you there and then have you guys discuss how recursion would play into this, but I'll go a little further. Okay. I want to leave you with how do we insert? And when I say leave you, I don't mean we're just going to leave. Like, we're going to get together and we're going to discuss. How do we insert if we need to get past this first node? And I am going to leave you there. So I wanted to use all these whiteboards. I think like 5 people. I really did not think all these people were going to come. Like, really, I didn't think you would all come. So I'm thinking like 5 or 6 people at 1, 2, 3, 4 whiteboards. Could be teams for 10 minutes try and come up with some pseudocode, or real code if you want to actually write out the code, of how we could insert. And then we can talk about it. Are people game? Yeah? Cool. Okay. I don't know, you guys could go in like rows. 1, 2, 3, 4, 5. 1, 2, 3, 4. Yeah. We also have these whiteboards for smaller groups. So, all right, this is the awkward part. Break. Go. Make teams, please.
I might have adjusted your camera.
Oh, that's okay. I'm going to edit this part out. So the question is, how does recursion, right on time. How does recursion help us insert into a tree? So yeah, you can erase my stuff up here. I'm going to walk around.
Oh, Darius. Hey, nice to meet you. I'm good.
Markers are up here. Markers, more markers. Erasers are here too.
Daniel and Sean.
So I think the approach we have like the current node, 5, and you're going to keep on updating the current node.
Can you use this one over here?
I agree. Go for it. So like, yeah, it's value.
Okay, so who wants to give it a go first?
9. Yeah.
Real code, or you guys can just have a 10-minute discussion.
I'll just start by like
only way to insert
class.
6 in here. And we call the function.
So at that point, are we saying, like after 5, are we saying, do we ask? Like, are we able to ask in that function, like, is there an existing node here?
Yeah, so
I see.
and then 9.
Yeah.
Check that will be the right
Because there is no node.
Exactly. So now we have
So 5.
so then since there is the right count, and now we
That's the recursion.
You get
So there's two children in the search tree is
So the first thing is if you have one,
So the first stage are
just what you need already.
check if there's greater than. There's a child recursion. Oh, you have a new current node. Check is it greater than?
Now that I think about it, it almost makes sense that you create
pop out.
So you're continually defining
pass a node in.
So like, for example, in this code you have like,
Just pass the node in. So for now though, we'll just have it, you pass the node in separately.
And I'm gonna do
Second,
that.
second step. But that's what I'm saying. You would pass a node
so
in.
again, like, it's greater than,
First, if there's
yeah, greater than less than.
actually,
Because there was no,
I think you would then check.
because if you pass nothing,
It doesn't have
just get, it'll get defined.
a child, right?
And this is BST node. So it could be other kinds of nodes too.
You would increment the object.
The node.
And then you would just go right back to the top, right? So you just do it over and over again.
But it's just going to two copies. So if that
You would need the pointers. It doesn't have a greater than pointer, doesn't have a less than pointer. No, doesn't have a pointer.
and in the
With that
constructor, these
pointer
will both be sent to you.
recursion.
Because again, you wouldn't necessarily have
that's
would get passed in. So the value is going to be
That's pretty much it. Yeah.
what is created. Probably would make more sense to use an actual syntax for this because it's a little complicated. But let's just say we have a node.
your mind
So,
language, your language.
we're going to recurse.
JavaScript,
Given a value. So that's where we're at right now.
So do we
Who
need to
knows how to
start?
put the node?
Yeah, we don't need to actually like
No, this is
declare
We didn't actually create a function yet. We're just kind of like what we decided. The first function we add on. So basically, it's going to be
Saying the node has attributes of left pointer, right pointer.
so you should. Yeah, actually, it would start if we extend, which would be versus like you put there. So you have try to like just write it out. Basically, it's just a thing. You just gonna say
So you're asking if version of all is small?
the key has a first value set to 5. We want to set it to this node.
Then we follow.
We actually want to do is guess function that we can just
Okay, it's not like that.
yeah.
It's not like
This is
that.
what we would do if it
Is it greater or less than? So you have to ask which point is less. Now it is less.
when we add we add
Oh, okay. Root is less. No, no is less
Like so each node.
well, it will definitely
You actually have something
to add text defined on the BST because it's just going to say
Node of value less than.
first we need to check it.
So the first thing we need to do
If it doesn't have a root, then we're going to use the root to the value.
so I think the good approach should be. Remember how we had to have a pointer?
We can just do it in this because
At the very beginning, that's the very first step. So what we do is
if there is a root, it's going to be a little more complicated, right? If there's
no root node, then we just do node, then we can just say this dot root. This is the slightly complicated. So in here we have to see.
But then you took out the.
Exactly. So we need to see first technically.
And then no to insert.
But you need to check to see if before you do current node. Before you assign the current node. What is that? It's assignment in JavaScript.
Yeah, so like for
So this is
It's like asserting.
you know like icons have.
So what do we do if this is
Okay.
well, that's assuming.
Let's go for like one more minute.
We don't know if, right now, if this is the root, it has a left and it has a right.
Yeah,
So
so
it's good.
I guess so. I'm saying if the current node is like this, then
Another node here, right? So we say, okay, if less than its value.
So when I try to,
So we go to
when I do let current node equals this dot root, it's null. I don't hit that. Or if it is null, then I'm in this if statement. Is that what you're saying?
yeah. So then now this is going to be null.
Yeah.
Make it really complicated logic, we can just.
Okay, so say the current node. So what are we doing now? We're doing the value thing.
And then so we have
That's
one.
If this node is like this, then
We don't want it to get too complicated, so instead of,
If there's no current node.
I guess what we need to do, one thing is,
Can you do if?
it takes a node, instead of just
So let's do
All right, we all come back together, get back in our seats, and
so-
let's talk this out. 'Cause I think everybody got to basically the same point, which was that I'm confused.
then we check.
right, instead of adding it to the root again.
it should be root dot right equals to n.
All right, so I saw a lot of things, heard a lot of things. I'm gonna ask you for some thoughts in a second. The main thing I saw was that most people got stuck after if this dot root equals null, right? We all got there and it was like, cool, if the root's null, cool, make the root equal to the node, sweet. And then it's like, shoot, what if it's not null, right? So what were some thoughts around what do you do if the root is not null? Yes?
So if the root is not null, right, then that's where the recursion comes into play because, you know, you're going to take, that's going to become your new current node. So I don't want to give away all the secrets.
Well, continue. What do you mean by this current node thing?
So you're going to have a method called insert, right, and it's going to take the node, the parent node, and then the node that you want to add, right? And that method's going to be called recursively, right? But you're only going to make that recursive call when you need to, and when you need to is whenever the node is not null. So, right? I'm doing a terrible job.
No, don't worry. It's not an easy thing, and I'm trying to get you to do my job right now. So the trick is yes, recursion. So let me see if I can diagram it for you. Right, let's assume we're inserting. Let's do those numbers I had before, right? What did I have? Like 5, 3, 7, 9. Those are good ones. All right, so I think we all got pretty much if the root is null, make our first node the root. Cool. So we have 5. Now, what to do if it is not null? Well, if it's not null, we need this idea of a current. That is a very powerful thing when doing trees. Who is current? Who am I? That's how I get called eccentric sometimes. But I think of myself in the tree, on the tree. However you want to think about being in the tree. I don't care how you think about it, but you yourself are traversing the tree. If you can go there with me, go there. Like I am moving along in the tree, right? So that is what I think of as current. Who am I? So we keep this current, I'll just do it C, and we start out, if our node, or sorry, if our tree has a root, then yeah, let's start at our current, at 5. Right? So I'm here. Now what do I need to do? What is important to me next? If I'm trying to insert 3, what's important?
You should check if it has any left or right values.
If, not quite yet. Not quite yet.
You check if it's higher or lower than the value.
Higher or lower, right? That's what insert is going to come down to a lot, is higher or lower. So we see that I'm trying to do 3. We say, great, I'm lower. Now is when we check. Do you have a right or a left? Right? Now, here am I. I'm current. Do I have a left? No, I don't. Sweet insert. Meaning, and by insert, I mean me, current, dot left equals node. We'll see this in code in a second. Great, let's do one that's greater, and then we'll get to one that's actually the recursive part. Okay? So now we say, okay, my current, or I have a root, my current is the root, my number is greater. Now I check, do I have a right? No, I don't have a right. Sweet. That's the happy zone. All right, now, and I think a lot of you got there. Now, a lot of you got there, but not thinking of yourself as current, still thinking of yourself as like this dot root. Nope, you're current at this point. Because current is going to change. It implies, right, that it is not forever. So now 9. Right? Rubber meets the road. We have 2 things in there already. So we say, okay, am I greater than, wait, what am I doing? 9? Yeah. Am I greater than the root? Yes, I am. Does the root have a right already? Yes, it does. Well, then what I'm going to do is insert, and instead of the root being where I start from, my initial current, I'll start from here. I'll start from the one to my left, because it's greater, or sorry, to my right, because it's greater. If it were less, I would start from the left. So now let's see what that does for us, right? So actually, I'm going to keep that up there. It's in a separate stack frame for any of you that really like recursion. You want to talk about the stack? It's over there. But now I'm calling insert all over again. But I have a different current. And I'll show you how to do this in code, but just stick with me there. I have a different starting place. And really, that's all insert is ever doing. It's only ever looking to my right and to my left. It seems like you have to go all the way down the tree to get there. You don't. You go one node at a time. So now, what I do is call, I don't know where to put it, I call insert on current dot right, in this case, because 9 is bigger. So let's do that. Now this is current, equals 7. I am 7. I look at the number, it is bigger than me. Do I have a right? No, I don't. Sweet, it goes right there. So, questions on that while I bring down this? Yeah?
Does that mean that we should put the insert method like on the tree class or on the node class?
Good question. Anybody want to take a crack at it? Do we put the insert method on the tree class or the node class? Why on the tree class? Yeah, from one, it just kind of like makes sense, right? A tree inserts things, a node doesn't insert itself. I like to just like think in plain terms like that. Like, what can a tree do? It can insert. Can a node do that? No. How can a node insert itself? But also, yes, that is, well, actually, that kind of is the answer. Yeah, is that the tree is the thing being inserted into, the thing that the root is attached to, so you put it on the tree. It is here somewhere. There it is. All right, let's get me up on the screen. Could somebody in the back, I think there's like a dimmer right there. Like you just press like it's a sun with a down. Yeah, not like all the way. That's probably good. Yeah. Gosh. Cool. All right. So where are we at? We're at insert. All right. So we're going to see the different parts of it, right? So we have a new node. That's the one that's going in. And then, because it's recursive, we're going to pass in this current node, right? And that was the act of us moving ourselves over. And that's what we wanted our new current to be. You can see, if you know ES6, I have a default of it is always the root. Right? And this was exactly what we said. If there's not a root, I could have also done if not current node. I'm gonna like refactor myself while I talk. If there's not a root, then the root equals the new node. Simple enough, right? We did that one. Now here's where the fun starts. And you can see it's actually not that long of a function after that. And it's the same thing twice. If my new node is less than the current node, if there's not a left node, make me the left node. And then return. That ends the recursion, right? If there is a left node, right? If it already has something that is bigger than it, then just move yourself to the left, make that your new current the next time around, and keep inserting the same node. So. Questions on the code part of it?
I have a question.
Yeah.
So in the case that there's two classes, a node class and a tree class, the node class is only creating objects with values, and the tree class holds the pointers and connects those values?
No, the node has the pointers. Nodes point.
Okay, so why do I have a tree class? What is the tree class doing? Just instantiating these methods?
Yeah.
Okay.
The tree class holds all the methods. So this is the node class. It's really boring, right? Super simple. Oh. Told you I was going to refactor. All right. Cool. So let's see it again. Right, and this is when it starts getting interesting, is when we're at 5, 3, 7, let's even do 9, and now let's insert 11. So, new node, I'll even kind of write them out. New node, and I'm just going to write the number equals, what did I say, 11. Right. So current node is this dot root. Current node, so that equals 5. So if there's not a root, there clearly is a root, so we're good because we've already done some inserts. So we're not there, we're here, right? If new node is less than current node dot value, which it's not, right? It's greater than, so we're going to skip over that one. We're going to go to here, if it's greater than. If there is not a right node, so I'm here, if I do not have a right node, well then that would be a good place to insert one, but I already have one. So do the same thing on that one. Move yourself there, and then look there. Hey, do I have something bigger than me? You can think of it that way. Right? And then we go, and important that we return, because otherwise we would get infinite loops. Maybe I'll do it on recursion. So now new node is still 11. Now we're at 7. New node is still greater. We go here. It says, is there a right? Shoot, there is a right. All right, we'll just do this again. Over here, run through. Now it's 9. And an important thing to realize is that in any given call of insert, you're only ever moving once. right? A lot of times people try to move through the whole tree. And you can do that with a while loop. I'm not saying you can't. It's actually harder to do that. In my opinion, it's actually harder. Because you're doing very simple things with each call of this function, right? All you're doing is checking, is it less, or is there a root? You always check that. But is it less than, is it greater than? And then, is there something that should be in my spot? Oh, there is? I'll do this all again, right? You're doing very simple things over and over again. So now we get to here, we say, hey, I'm bigger than you. Do you have something that's already bigger than you? No, you don't? Cool, I'll be that person. And I'm happy. Yeah, question?
Yeah, it's just, wouldn't you insert 9 on the left of 7?
Nope, because 9 is greater than 7. So, important thing to point out here, because I don't want you going off thinking that this is the end-all, be-all, end-all, is that this will not always give you the nicest tree, right? You can already see that this isn't like the nice, pretty tree that I gave you before, the one that's over there. Yeah, I'm going to pause on this. Can we bring the lights up a little bit again? So that is a topic for another time. How would you insert and yet keep the tree balanced? That's a much harder problem that I encourage you not to try to solve. Don't try and solve that problem. It's really hard. Just insert really easy things into the tree and work up to being able to do more sophisticated things like that. You'll see you can still do cool things with trees, not having that really nice insert that keeps things balanced. So don't really try it. That happens a lot. That was what a lot of our curriculum was like. I don't know about the curriculum you guys have seen, but it's like, do all this shit with all the different, everything you can do with a binary search tree. And when I was reading it, I was like, this is way too much. It's too hard. Just do really simple things. And then you can build up, and right, the simple building blocks make the harder thing not seem so hard. So that's my encouragement to you. Is just figure out how to build really unbalanced trees. That's fine. It's fine for right now. But just get that recursion step in place. Okay. Now, let's talk about how we would search one of these suckers. So, who has implemented a depth-first or breadth-first search in their life? Ever? Who remembers how to do that off the top of their head? All right. Brave people. Sounds good. So, we're going to do it with our tree. And we're going to talk about how that is done. So I'll give a description of what a depth-first search is. Again, I think it's really important in searching and traversing the trees to imagine yourself in the tree. It might sound stupid, but imagine yourself as being on the tree. I want to make bigger numbers. So we have a nice tree. Let's just assume that it's already there. We did our insert and it balanced it perfectly, and we're really good. So we put in 50, and we put in 25, 75, 15, 35, 85. And at its heart, there are lots of different implementations of depth-first search. You could just be writing a function and expecting it to say true or false, right? Is this thing in my tree? Maybe that's what's important for the application that you're working on. Is this in my tree? You could also write a depth-first search to say, get me that thing in that tree. Search for it and retrieve that thing in that tree. That might be important to you. The cool thing is that they're the exact same for those two. Right? All you have to do is get to the node. So depth first is going to do this. I'm going to draw this thing out here. I'm just going to make it like a big blob. And this is going to be called a fringe. Has anyone heard this terminology before when making trees, or sorry, when traversing trees? Gonna blow your mind. So please focus on the fringe part. So what am I gonna do? It's a tree, right? I only have one place to start. I start at the root. I can't start anywhere else. That's really another fundamental thing. You always start at the root. Just never confuse yourself, you always start at the root. So, I'm at the root. Depth first search is gonna say this. Okay, look at my children. Put them in the fringe. Take that, that's given. Put it in the fringe. Now what would I really do? Depth first is trying to go down the tree. Go down, in a systematic way, go down the tree. So let's say I'm searching for 65. Let's just say, right? I'm going for 65. Maybe I should make that a square. Going for 65. This is what's going to happen. I'm going to look at my root. I'm going to say, is that number? Nope, that's not what I'm going to do. I'm going to say, put my children into the fringe. Now, a little bit of magic. I'm going to choose 25. There's a reason we're going to choose 25 for depth first search. But I'm going to take it out of the fringe, and now who I am is 25. Am I 65? No, I'm not. Well, let's put my people into the fringe. That's wherever. But you can kind of see the pattern I'm going in, right? I'm kind of going down and to the left. So, okay, let's put 15, or let's now do 15. Am I the number? No, I'm not. Am I greater or less than? It really doesn't matter. Am I the number? No, I'm not. Okay, cool. Well, do I have any children? I can't put any children in the fringe. Okay. So maybe let's go here. Maybe 35 is next. Nope, I'm not the number. My children aren't there. Only one left is 75. Have you ever had trouble getting to the other side of a tree? We just did. Okay? And I'll show you how. But notice that we just got to the other side of the tree. That's often really hard for people. Like, how the hell do I go? I can go left. Going left is easy. Right? Oh, what is that? Zoolander, right? Left, something like that. That's easy. But how do I get to the other side of the tree? Well, I just did it by magic, right? The only option left is to go to 75. It wasn't any of these. So, is it 65? No, it's not. Okay, well let's put our children in there. 65, 85, wasn't 75. All right, cool. Well, I kind of went to the left before, so let's keep that general idea going. Cool, I'm 65. Hey, I'm there. Right? Return true, return the node, whatever you were trying to do in the first place. It didn't seem random, right? And it wasn't. It was an algorithm. Right? Now, I think move, right? We've talked about moving, which is just setting your current to be your left or your right. That's not too crazy. Then we did this other thing involving the fringe. So let's talk about why, or how I can make a fringe such that I move in that order. Anybody know what data structure I need for that? Not you did. A cube? Anyone want a different one?
An array.
An array?
Stack.
Stack? Matrix? I don't know about a matrix, to be honest. It's too many dimensions for me. Pretty linear. Yes, it's one of those answers. It is not all of those answers. It's distinctly one versus the other. And it is a stack. So let's look at it now as if it's not a big blob, but in fact a stack. Okay. So here's my fringe. It's a stack, so I'm going to put things here and stack them up. So, start at 50, put 50 in my fringe. Great. Am I the number? Well, you put it in and then you take it right out. There are a couple, you can start it with it in the fringe, you can not, I'm not going to go into that. Basically, I'm at 50, I am 50, put my children into the fringe. Now, yeah, I'm going to put the right children in first. wait. Yeah, I'm gonna put the right children in first. That's just the convention, that I'll just put the right children into the fringe first for depth first search. And then I'm gonna put 25. Okay. And then I'm 50, right? And I go, am I 65? No, I'm not. All right. Take something out of the fringe. Pop off the stack. Okay. 25. Am I 65? No, I'm not. Okay, well, I'm already out of here. Sweet. Put my children in. Right, left. Are we seeing that this is actually what I was doing before with the big circled blob? It's bringing me down the tree. It's putting my children at the top of the stack before, so that they come off before my siblings. Okay? This is going to come off before my sibling. Cool, 15, no children. 35, no children. Hey, I moved to the other side of the tree because that was the only thing left in my fringe. 65, 85, 65, pop 65 out, and we're all happy. So there are two things going on here. There's a stack holding all of the elements in our fringe. And there's recursion going on again. Okay. The recursion was, oh, you're not me? Or I'm not what you were looking for? All right, well, go check this one. Go check the next thing off of the fringe. Go check that one. Maybe that's it. That's maybe how you can think about it. Okay. It says, oh, you're not 50? Well, call depth first search. Why don't you search and see if 25 is? Well, it's not. And I'm not going to go all the way down the tree again. But, oh.
65.
25, 75. Oh, yeah, 50. No, 35, 15. Because you put 25 children into the fringe. So, I want to see how much time we have. And, all right. Would you rather, let's do a poll, would you rather see the code and move on to remove, or talk in groups about the pseudocode of how to do this for like 5 to 7 minutes? Raise your hand for pseudocode. Okay, raise your hand for seeing my code. All right, that one won by a little bit. Those that didn't vote, you have to leave now. Just kidding. Can we dim the lights? All right. There it is, in all its glory. Shoot, that goes kind of long. So, always have a current node, a sense of who I am on the tree. I don't know, there might be different ways to think of it. Like some people might say that that's a really bad way. It has always steered me right. So if I could get you to get this idea of I am a certain place on the tree and I only have 2 options to move, changes. I think it's a game changer. So you can see current node is either current node or the root. Why did I do that? I could have used, I don't know what I was thinking. But if current node equals value, great, right? This is an implementation where I return the node itself. I could have returned true, right? If all I cared about was true or false. But right off the bat, right? This is called your base case in recursion, right? If I found what I wanted, great, return that. That's good to go, right? If there is a right, put on my right. If there's a left, put on my left. Put it onto the stack. Yes?
It's a question on that one. Why wouldn't you do a comparison as to whether the right or left was greater than the number that you're looking for, and then only go down that side of the tree?
that may optimize it. Let me think. I think you could still like. I'm thinking of like if I'm searching for 100. Yeah, that might be an optimization. I really didn't try to optimize, like intentionally didn't try to optimize. I'll think about that one. That is a good point. Like I said before, like I was trying to shave away like and just make it really basic. But that's a really good point. So instead, we just put them both on there. Search everything. We're searching all the way through. I gotta think about that one. And then you can see I actually do use a while loop, but it's kind of different than you might think, right? It's just while the fringe length is greater than 0. So while there's something in my fringe, keep looking at things in the fringe, is what that while loop is saying. While there's something there, keep looking. So new node to search, right, is give me the thing off the fringe. It's really simple. That's a really nice thing about the fringe. It's just like, hey, give me the next thing. And once you see why it's a stack, which hopefully at least like some of you, I kind of saw some nods and some smiles. Once you see why it's a stack, it's like, oh sweet, so I just have to get this thing. It keeps track of where you should go next. You no longer have to care. Your stack takes care of it for you. And then return from search, depth first search. So this little trick is, why did that? Yeah, if we actually get something, as opposed to just undefined, we'll actually return it. This should be null. Sorry. And otherwise, if we get all the way through the fringe, then we haven't found it. So just return null. So, questions on that, and then I'm going to kind of deviate from this because I didn't end up holding to the like 20 and 10, 20 and 10 that I meant to do. And we're almost out of time because I want to get to questions at the end. Does anyone have questions on depth first search? Okay. My question to you, yeah, can we put that up? Or sorry, can we put the lights up again? Thank you. You guys get extra snacks. My question then is, what's different about breadth first search? And some of you may just know the answer to this because like you were studying and you're like, oh, it's so easy. Why there's how the difference is. Anyone? Yeah.
Instead of going vertically down, it goes horizontally across.
Right. How might we achieve that? The answer is all in the fringe. Right? So let's instead of seeing this stack, see it, yeah, we can leave that, as a queue. Okay. Here's my fringe. Q-U-E-E. No matter how many times I write Q, I always think I spell it wrong. So, start off with 50. Okay. We're going to do the same thing, but as you said, we're going to try and go horizontal. So which one do I want to put in? Just to make things more interesting, I'm going to put left in first. It's not really going to matter all that much. No, yeah, oh, sorry. So 50, not my value, obviously. So let's put 25 in, 75. This is the front, if you like to think of it that way, of the queue. Right? It's the first thing that was put in. Right? Lots of different ways to imagine a queue, backwards and forwards. This is where I used to get lost with people. It was like, what? Which one is the front and the back? So this is the front of the line. 25 went in first, then 75. And then because 50 wasn't it, we took it out. And then we're like, okay, well, what about 25? Right? And we're looking at 25. Like, no, that's not the value. Shoot. All right, well, let's put in my children. And I did left first. Yeah. So let me put in left, right. And it's like, nope, okay, that one's not it. Let's try 75. Nope. Not it. Put in left and right. 65, 85. And now, we're going to get there, right? Now we're going here. Now we're at 15. Notice we went here, 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 here. 15, not it. 35, not it, and has no children. 65. Almost like magic, right? It's the same algorithm. Same exact algorithm. You just change the fringe. Yeah?
Does it make a difference if the first one's using first in, last out, and this one's using first in, first out?
That is the exact reason why it's working this way. Right? That is what gives them the two different behaviors. Now, we can talk about big O of this, implications for your time and space complexity. I don't want to go there, right? That stuff, that's the stuff I'm shaving away. We're just trying to implement right now. Because I think you need to implement before you can understand that stuff. A lot of people put it the other way. Maybe there are benefits to doing it the other way. But to me, you got to understand how to make it do the thing before understanding all the crazy characteristics that come out because of it. So again, use a queue to get yourself through the tree horizontally. And if you ponder on that a little while, it'll start to make sense, right? And I wouldn't expect you even right now for me to be like, oh, which one is DFS? You're like, oh, I don't know, queue, stack, tree, I don't know, right? But if you think about, and hopefully you know a bit about stacks and queues. I almost made this lecture, stacks and queues, to be like the kickoff of mine. I was like, no, I think stacks and queues are, people at least hear LIFO, FIFO, and they're like, okay, I can figure it out. And I think you can go from that. If you just know LIFO and FIFO, I think you can really understand the power of what they're doing here. Right? They're saying which, because you also understand the concept of the fringe, right? Who should I explore next? Who should I be next? Where should I go next? Whatever one of those resonates with you, think of it that way. The fringe, if you have a stack, is saying this one, then that one, right? Like all of the further down things. It's very greedy. It's saying keep going and put these new things on and make them really important. Make them the ones to go to next. There's a queue. It's like no. Let's all get in line, right? Go across. Yeah. And whichever child comes next, go to that child. Okay. So, my goal was to finish by 7:40 and then open up for questions. 7:28. So, I want to show you, hopefully, sorry, one last time, guys. Can we get the lights? Why this might be cool. And I'm super bummed. You have no idea. It was 1 in the morning last night, and I broke it, and it doesn't work. 100%. It works almost perfectly. But basically, what I made is binary search tree that takes strings that are converted to integers. Now, the limitation is it can only be 5 integers long because I couldn't come up with a good enough algorithm to do all strings. But here, I'll show you. It takes in a string, converts it to an integer, such that things with small, closer to A and with, just closer to A, have smaller integers, and things closer to Z have bigger integers. And we can already see how that really lends itself to a binary search tree. So I told you at the beginning, if you have a tree, 50, 25, 75, whatever, 55, whatever, 15. You can traverse it in such a way, it's a depth first search, that you go, here I'll also do 27, that you can count 15, 25, 27, 50, 55, 75. You can make it do that. Save that for another time, or you can read the code. But what that does is if these are all strings that have numbers where A's are way down here and Z's are over here, and everything else is in the middle, if I get them in order, then I have it sorted alphabetically. So that is almost, well, it's sorted alphabetically, I just lost 4 letters, is all. So you can see it goes AC, and it's just right off the bat, it pisses me off. But, right, I put all these in, and here are their integer values. And now I just have to get more words and get those freaking B and C, or B-O, it's B-O-H and something else. I have no idea where they went, but it was too late last night. So, I'll show you the code. So I just have my regular binary search tree, but it has this method. Retrieve all in order. So it's very similar to, you may have heard of an in-order depth first search, pre-order, post-order. So this one's just in order, right? And so I don't want to go into this one, but this is what's getting things in order, right? Nope, here it is, string to integer. This is how I'm switching it into an integer. Basically what it does is it gives a lot of weight. Data science people are gonna know this probably better than me. It gives a lot of weight to the early letters, and it gives a lot of weight to the earlier letters in the word, but smaller weight to A's, B's, and C's. So if you look at the alphabet part of this, which is here, right? A is only worth 1. It's all plus 26 so that you don't get any collisions. But A is 1, 2 is B, or B is 2, all the way down. So Z are really big numbers. You take that, string it P, you get that number and multiply it. First, this starts out at 10,000, and this is why it can only be 5 letters long, is it starts out at 10,000, then orders of magnitude down from there. And this part was gonna just mainly be hand wavy anyways. It works. All the numbers come out. This wasn't the main part of the presentation, but there it is. And then you just insert them into the tree. And this is really ugly code because I didn't use Webpack. But seed tree. Basically, you binary search, type insert into binary tree. So you may have come here thinking that we were going to do binary search and been surprised by this entire presentation. So binary search is different. It's just binary. That's why they, and you're searching. So they sound very similar. Binary search, which many probably know, is you have a sorted array, sorted list, whatever language you're using, and you successively cut the array in half, looking to see if you found the variable, look if it's greater or less than where you cut, and recursively cut down. So you do a similar thing to make it a balanced tree to start. So I just took all the letters and just basically did a binary search kind of insert on them, and it starts with M, puts M at the root, then it's like F or something is the next one in the middle, and built the tree, seeded the tree that way. No binary search left. That's all there is to that. And then I just made a table out of it. So that is what I hoped to prove to you is somewhat useful application of all the crap we've been talking about tonight. I know I don't ooh and ah you with it, but that is something you could very well do. Look, how many people graduated from their program less than a year ago? Less than 2 years ago? Yeah. So I graduated 2 years ago. This was super fun, and I don't know if people are still searching for jobs, already have jobs, whatever. Like, I was in your place. I still am in your place, right? I'm still a boot camp grad. Like, it's all stuff that is available to us that I don't think was necessarily taught to us. Right? We did Rails, did Express, did React or Angular, right? We all did that stuff. But you can, and then like 1 week of computer science. You can do the cool computer science stuff, make it simple for yourself, and then just build a simple little interface for it, right? Like this all lives, all the hard work I did on binary search trees, you can't even see it. And ideally I won't even have, I'm not even gonna have integer here, I just did that purely for myself. Like this is, you know, a cool little thing where people can put in words and, you know, make it alphabetized, and maybe I'll throw a backend on there, or make it local storage or something, right? I can build from there, but it's much more fun. This was much more fun to me than like Rails GNU or NPM init, right? And like, okay, I'm gonna build another CRUD app. Like we all did a lot of those, I'm sure. I don't know about exactly how all of your programs were, but I know the general gist. Like, I don't know. This stuff is much cooler to me, and you can hopefully see, like you can put the two worlds together. I just wanted you to see that they're not so far apart, that my web development now, right, I got some JavaScript chops that help me be able to do this, but then I was able to put it into an interface, really simple interface, but still, that's the general thought, is do this cool stuff that like our data science people usually do. I know it's not data science at all. I'm not trying to belittle data science, but closer to that type of stuff, and then just put a web application on the front of it. There's way cooler stuff going on behind the scenes. So that's all I got for you. If there are any questions. Okay, then, wait, Dave, what's up?
Yeah, it's just like, I can, you know, like with trees in general, I can always think of plenty of uses for them, you know, like bioinformatics or the file transversal in your view system or whatever. Like, what else do you use actual binary solutions for?
Yes. Alphabet. Honestly, this is the one I could think of. It's hard. It's hard for me to think of an actual use case of binary search trees. You know, like the easy answer is like, yeah, they use them in way lower level programming languages and to do very meaningful things, but it's hard. It's hard to think of that, and I think that's often why it's hard for us to learn them, is that it's like, you know, you're just saying left and right, Parker. Like, I really don't care that it's left and right. You gotta search a little bit for it. And by all means, please copy me and do this exact same thing. Yeah.
That's how they do indexes on databases? Yeah.
That's a big deal.
There you go. Any other questions? All right, well, thank you for coming. I'll stick around for a little bit if anyone wants to like ask a question or something. But yeah, thanks for coming. Look out on Andrew's, is it like a Galvanize, Learn to Code something meetup that you guys all saw this on? I'm not sure where you saw it, but look.